today, just do it as quickly as you can so you don't get behind. So what we're going to do now that we've had a little bit of a review for integration techniques in general is we're going to start chapter 6. Chapter 6 is a compilation of applications of integration. There are way more integration techniques and applications than what we will do, but we're going to look at a few of them. We're going to kind of revisit the relationship between acceleration, velocity, and position that we talked about a bit in Calculus 1. We're going to talk about areas, and those two things we'll do today. And then on starting next week, we will talk about volumes of revolution, which are really cool, work in the physics sense of the word, and a few other applications. This is one of my very favorite chapters of this book. These are so cool. Okay, now, what we are going to talk about first, though, goes back to some things that we talked about in Calculus 1, particularly the relationship between velocity, position, and acceleration. If you have an object moving along a line, remember most of the time we call position S of t. So that just tells us the position of that object at any time t in its travels. And we learned in Calculus 1 that if you take the derivative of position, you get the velocity function. Now remember, velocity is basically directional speed, right? Speed's always positive, but velocity can be positive, negative, or zero. When velocity is positive, you're moving in a positive direction. And depending on whether you're talking about oriented up and down or sideways, when velocity is positive, you're either moving to the right or up. When velocity is negative, you're either moving to the left or down, depending on whether it's horizontal or vertical movement. Then if you took the second derivative of position, or in other words, the first derivative of velocity, we got the rate of change of velocity, which is acceleration. Okay, so these things we did work with a little bit in Calculus 1, and we're going to do some similar things that we did then in section 6.1. So just as a reminder, and I know I wrote part of this down already, but velocity is nothing more than the derivative of position, and displacement, remember, displacement is actually the difference in position when you start versus when you stop. So let's say we have an object that's moving along this line, and this is its initial position. Okay, so that's the position at t equals 0. If that object moves to the right 2 units and then turns around and comes back and stops at the exact same spot that it started, what's its displacement? It's 0. If I start and stop in the same spot, my displacement will be 0. It's basically the net of your distance traveled, okay, away from your original position. So in general, displacement is going to be position at the ending moment of your time interval minus position at the beginning moment of your time interval. But due to the relationship between velocity and position, if you integrate the velocity function, since it is the derivative of position, you'll get the position function. So S of B minus S of A is nothing more than the definite integral from A to B of your velocity function. So that's a quick way to find displacement. Well, I say quick, relatively quick. Distance traveled, on the other hand, if we started with that same little object that started here at S of 0, and it moves 2 feet or meters or inches or whatever to the right, and then it comes back and stops at its initial position, how many units of distance did that object travel?
4.
4.
4.
Exactly. But in displacement up here, what went right then canceled off with what went left. So our displacement on this same little trip was 0, but our total distance traveled is 4 units. So In general, when you're taking to find distance traveled, that will be the integral of the absolute value of velocity. And that will keep us from canceling off when it's going right versus left or up versus down. Okay. Okay. Now, another thing that you want to keep in mind is another name for the absolute value of velocity is speed. All right. While velocity can be negative, speed cannot. So this is all in the definition part of your text in section 6.1. So if you don't have these printed off or copied down, you still have access to this exact box in your textbook. So let's look at an example. Now, one thing we want to keep in mind, let me go back here just for a second. If you have a function, now I'm going to call it a velocity function just for fun in this case, because that's kind of the application that we're going for. But I want to remind us how integrals are related to area, because that's going to be really important. Okay. When your function is non-negative, in other words, at or above the horizontal axis, in general, the integral of that function over that interval is equal to the area below the curve and above the x-axis, or in this case, the t-axis. Right? That's how we basically kind of motivated the idea of definite integral. But if your function's non-negative, area and definite integral, they're the same thing. We also know that this integral for velocity functions is equal to displacement, right? When your integral is of a function that is completely below the horizontal axis, oops, this would be from B to C. So if we're looking at the integral from B to C of this function, that's going to be the negative of the area between the graph and the horizontal axis. Okay, so if I asked you what the area of this region is, we just take the integral and take its negative, or in turn, we would take the integral of the negative of the function. In the most general sense, when we integrate just from A to C of V of t dt, we get what we call the net area between the function and the horizontal axis. In this case, it's a t-axis, but it could be a, an x-axis if we were talking about x as the independent variable. Now, what do I mean by net area? Well, remember, this integral is displacement, and what it is it takes the area here that's above the horizontal axis, and it would subtract off the area here, which would be below the x-axis. So net area is always equal to the definite integral. If that function is also above the x-axis or the t-axis, whatever you're calling the horizontal axis, the area between that graph and the t-axis is equal to the definite integral. And if it's completely below, you've got the negative of the area. If it crosses somewhere in between, well, you're going to have something in between. In other words, what we call net area, where you've got some of it being positive, some negative, and they're going to be canceling each other off. So I say that to remind you, because they're about to give us an example where we are given a velocity function on a particular time interval. And so they tell us our velocity function is of an object moving along a line. Time is measured in seconds and distance is measured in meters. And it says the areas of 4 regions bounded by the velocity curve and the t-axis are also given. So between 0 and 2, our velocity function is completely negative, and the area of the region between that velocity function and the t-axis is 20. Between 2 and 4, our velocity is positive, and that area is 14. 4 to 6, it's 10, and 6 to 8, it's 6. So first question, I'm going to rewrite up here because my ink was getting a little bit low before I changed it this morning. On what intervals, I should say, is the object moving in a negative direction? Now, the object moves in a negative direction when velocity is negative, because remember, velocity is basically directional speed, right? It tells you not only how fast the object is going, but also is it moving in a positive direction or is it moving in a negative direction? So if you're looking at this graph and you want to know when velocity is negative, now remember our velocity function is what is being graphed here. Velocity is negative when it is below the horizontal axis. So it would be negative between 0 and 2, and between 4 and 6. Now, why did I leave open parentheses on these endpoints rather than writing from 0 to 2 and from 4 to 6?
Because the point still exists?
It does still exist, but specifically, what is velocity at those endpoints? When t is
continuous movement?
I'm not asking my question very well, I don't think. That's true, but what's the value? That's what I should have said. What's the value of velocity at t equals 0, t equals 2, 4, and 6? What's
0.
the 0? So at those endpoints, our velocity is 0. So we're not moving at all, are we?
Right.
Exactly. So we leave those endpoints out because those particular t values are not when our velocity is negative. Those values are actually when our velocity is 0. So specifically in this particular case, our velocity is changing from negative to positive, say at t equals 2. So we're going from to the left for a while, and then when we hit t equals 2, we turn around and go to the right, or down versus up, depending. Okay. Is everybody okay so far?
Yes.
All right. So next question is, what is the displacement of the object over the interval from 2 to 6? Now remember, displacement is just the definite integral from 2 to 6. So we're going from here to here. And since they didn't give me the actual, definition of this velocity curve, they just showed me the graph. We're talking about the net area between 2 and 6. So that would be 14 positive, because that's where it's above the t-axis, and then minus 10 for the area below. So we would get 14 meters, or 14 minus 10, pardon me, is 4 meters. Now, does the positive value of this make a difference? Yeah.
Yeah.
If you have a displacement of 4 meters, let's say your object is moving horizontally. If this was S of 0, then what that positive 4 displacement means is that your ending point is 4 meters to the right of wherever you started. So if that had been a negative 4, that would mean I ended up 4 meters to the left of wherever I started. So it is important to notice that that's a positive 4. All right, so what about total distance traveled? Between 0 and 6. Now remember, total distance traveled is going to be the same as the area of the absolute value of our function. So between 0 and 6, if we took the absolute value of that function, this guy would just pop up here to the positive version of that. This would pop up here. So the area for this part would be 20. Between here, it's 14, and here to here, it's 10. So our total distance traveled will be 20 plus 14 plus 10, or what, 44 meters. Displacement from 0 to 8. I want you guys to try this one. I'll give you a couple of thinking minutes. If you're looking at this picture, what do you think the displacement would be on the interval from 0 to 8? I'll let you look at that for a second, and you can either just tell me when you're done, or you can type your proposed answer in the chat, and we'll go from there. All right, awesome. I'm sorry about the ink on that. I hopefully have it fixed before next time. But displacement between 0 and 8, that's just going to be the equivalent of the integral from 0 to 8. So between 0 and 2, we would have a negative 20. 2 to 4, we've got 14. 4 to 6, we've got negative 10. And 6 to 8, we have plus 6. So we would have what, negative, you said negative 10. Okay, excellent. So that would be negative 10 meters. So after 8 seconds, what that means is our object is 10 meters to the left or below, depending on whether it's a horizontal or vertical linear movement of its starting point. Now, if I had said the total distance traveled between 0 and 8, what's the only difference we would do here? Instead of subtracting these, we would add them all together, because we would be doing the the integral of the absolute value. So if I needed total distance traveled, on 0 to 8, we would have 20 plus 14 plus 10 plus 6, or what, 50?
Yep.
All right, last question off this particular problem. It says describe the position of the object relative to its initial position after 8 seconds. Now we just did that part. Since our displacement is negative 10 meters, that means that the object is 10 meters to the left of initial position. Or if it's a vertical movement, it would be 10 meters below. Okay. Now, in general, if you want to find your position, let's say I told you S of 0 is 4 meters. So we started at 4 meters, and I want you to find the position of the object at t equals 8. So in other words, after 8 seconds, where am I? Well, I started at 4, and during those first 8 seconds, I went 10 meters to the left of 4. So where would I be?
-6 meters.
-6, exactly. So my position at 8 would be 4 minus 10, or -6 meters. Or in general, to find position at S of B, for instance, I mean, I just picked B kind of randomly, but you're going to take your initial position plus the integral from 0 to B of V of t dt. Now, we had it figured out a little bit more easily. We'd already done all the work, so we didn't want to integrate it separately. We know this particular part is just your displacement over the interval from 0 to B. Add displacement to initial position, and you'll get your position at that time. And I know for those of you that have had physics, this is probably kind of old hat, but if you haven't, then well, maybe a little bit different for you. All right. Go ahead. I'm sorry.
Can you explain? I get the -6. Where did that come from?
If I told, this part wasn't in the original problem, I just gave it to you. If I tell you that your initial position is 4 meters and I ask you to find your position at t = 8, well, if you started at 4 meters, to find your position at t = 8, you're just going to take your initial position of 4 and add your displacement over that first 8 seconds. We had already found our displacement over the first 8 seconds was -10 meters. So we just have the 4 plus a -10 or -6. Did that answer your question?
Yeah, thank you.
Okay. All right. So this one, they were kind of nice to us and actually gave us the values of the areas. Sometimes they're not quite as kind, and we have to do that ourselves. Okay. So this is a second example from the same section. I'm going to give you just a minute to write down a copy of this graph if you want it. This is going to be 1, 2, 3, 4. Okay. And this is our velocity function. Making it a little darker. All right, they want us to tell them what the displacement is between 0 and 10. Now, before we figure it out, can you tell me, do you think the displacement will be positive or negative on the interval from 0 to 10?
Be positive, I think.
Positive.
You're right, it's going to be positive. Why? Well, there's a whole lot more area that's above the t-axis and below the graph than there is area below the t-axis and above the graph. So in other words, the velocity function is mostly positive on this time interval. So we're expecting a positive displacement. But to find that positive displacement, I'm going to need to figure out the area between the graph and the t-axis. Okay, we're going to just use geometry. This part, this area, I'm going to call it A1. That is a triangle whose base is 1 unit wide and height is 4 units tall. So that area would be 1/2 the base times the height, or 2 units. Okay, or 2 square units since we're talking about area. So this will be A2 for just this little triangle. Now, what about this rectangular part right here? That's going to be my A2, just for future reference. That is a rectangle that goes from t = 1 to t = 4. So it's 3 units wide and 4 units tall. Since it's a rectangle, to find that area, it's just going to be 3 times 4, or 12. Looking for a different color pen. Hang on just a second. Okay, I have 473 pins and can't find a single one that I want. Okay. What about this one? This is going to be our A3. That's still a 1/2 of a 1 unit wide and 4 units tall. So that's going to be 2 units as well. Now notice this half of this triangle that's below is, it goes 1, 2, 3, 4 units down and 1 unit wide as well. So A3 and A4 are going to be the same size. Okay, it's just one of them's up here, one of them's down here. What about A5? It's the same, isn't it? It's still 1 unit wide and 4 units tall for the triangle. So A5 would also have an area of 2. If this is A6 and A7. All right. A6 goes from 7 to 8 horizontally and from 0 to 4 vertically. So A6 will also be 2 units because it's 1/2 of a triangle that is a 1/4. Okay. The triangle is 1/2 of a rectangle that's a 1/4. All right. And so let's do the very last one. A7.
Would that be 4?
Yes.
Let's see, it goes 2, yeah, it will. So it'll be a 1/2 of a 2/4 or 4 square units. All right, so if I take this entire region here, all of this first area between 0 and 5, the size of that area would be what? It'd be 2 plus 12 plus 2 or 16. Good. So that entire region right there, found the pen bucket. Ooh, between 0 and 5, sorry. The area is 16. Okay. 2 plus 12 plus 2. Between 5 and 7, this area, which is A4 plus A5, the size of that area would be 4. And then between 7 and 10, we would have 6 and 7. So that's going to be 2 plus 4 is 6. All right. So we did all the hard work here. Now let's see what of the questions we can answer. So part A, what is the displacement between 0 and 10? Well, it would be 16 minus 4 plus 6. Or 22 minus 4, which is 18. Now, this may be in terms of meters or inches or whatever. It didn't specify in this particular problem what the units of measurement were. Now, is everybody okay right there?
Yep.
Yes.
Does anyone have any questions about how we got these perspective areas? We would have been out of luck if it hadn't been nice geometric shapes, since they didn't give us a formula, but anyway. All right. What about the distance traveled between 0 and 10? What's the only difference? Instead of subtracting off the 4, I'm going to do what? Add it. So we'll take 16 plus 4 plus 6 is 26 units, whatever that may be. Okay. The position at t equals 10 is the initial position plus the displacement on the interval from 0 to 10. In the statement of this problem, they told me that the initial position was 1. So we will have 1 plus the displacement was 18. So we'll have 19 for our position. Okay, sorry, it kind of ran together there. So you just take your initial position and add displacement on the interval from 0 to whatever this t value is. And the reason I kind of squished all that up in the top was because this last part, there's quite a lot to it. All right, they want us to find a piecewise function for s of t. So what we're going to do is we're going to first of all find a piecewise function for v of t. And then we're going to use our relationship between velocity and position to find position. All right, so between 0 and 1, my velocity function is this little line segment right here. That is a line with a t-intercept of 0 and a slope of 4 because we move right 1, up 4. So for that interval, our velocity function will be just the line for t. Right? Between t equals 1 and t equals 4, what is our velocity constantly at? It's just 4, isn't it?
Yeah.
Yeah, so
Yes.
it'll just be a constant 4 on that interval. Next, we're going to do this linear chunk right here. That line starts at t equals 4. So I'm going to go from 4 is less than t to less than or equal to, what is this, 5, 6?
Yes.
I need to find the equation of this line. Okay. Remember, as long as you know the slope and 1 point on the line, you can figure out what the equation of a line is. Okay. So what's the slope of this line? Well, we go right 1, 2, and we go down 8. So the slope of that line is -4. Does that make sense?
Yep.
All right. So for the black part between 4 and 6, the slope is -4. So we would have y equals -4t plus b. To figure out what that b is, or the y-intercept of the equation of this line, we just need to pick a point on that line segment and plug it in. I'm going to plug in the point 5, 0. Okay, and why do I use 5, 0? Just because 0 is easy to plug in. You could use the point 4, 4 if you want to, or 6, -4, any point on that line part. But I'm going to use 5, 0. If I replace y with 0 and t with 5, I get that b is equal to 20. So on this line segment, my velocity function is -4t plus 20. Then I need to do the same thing here. Okay. So this will be between 6 and 8. What's the slope? Well, between 6 and 8, we go from -4 to +4. So we go up 8 units and we go horizontally 2 units. So my slope there is +4. And just for a little extra practice with that, 1 point on that line segment is the point 70. So I will have y equals 4t plus b, and if I replace t with 7 and b, or pardon me, y with 0, I can solve for b. So I'll get 0 is equal to 4 times 7 plus b, or b is -28. So between 6 and 8, our velocity function is 4t plus -28, or I'm going to write it as 4t minus 28. And that's from 6 to 8. Last one, okay? I want you guys to take a couple minutes and figure out what the equation of this last line segment is, okay? And then we'll compare. So this is going to be between 8 and 10. And I'm not going to show you mine right now because I want you to get a chance to work on it for a minute, and then we'll compare our answers. All right, are you getting an answer?
Yep.
What'd you get?
Got negative 2t plus 20.
That's what I got as well. Because we know our slope between 8 and 10, we go down 4 units and over 2 units. So our slope is negative 4 over 2 or negative 2. And one of the points that's on that line segment is 10, 0. So I just plug in 10 for t and 0 for y and solve for b.
Can I ask something real quick?
Of course.
So I'm having trouble, like, I don't know how to find the slope, like m.
Well, there's a couple ways we can go about it. I've just been counting, but let's just look at it for this particular line segment that since this is
Yeah,
the
for
one that we're
example,
working
from 4 to 6, I don't see where the -4 comes from.
Oh, okay, from 4 to 6. Okay, so notice that this is the point 4, 4, and this is the point 6, negative 4, right?
Yes.
So to find the slope connecting 2 points, you just take the difference in the y's over the difference in the x's.
Rise over run.
It's just the rise is y2 minus y1 over x2 minus x1. Now, what I was doing is I was just counting. I was going, okay, from this point to this point, we went horizontally, we moved 2 units, so that's my run, and we moved down 8 units, so that's my rise. So I got a negative 8 over 2 is how I was figuring my slope, but you can do it with the formula as well.
Oh, okay, gotcha.
Okay.
What about for the 4 that is constant? It's just because it's a straight line, so it doesn't
Yeah,
have
just because it's a horizontal line, the y values are constantly 4 across there. Yes.
Thank you.
You bet. And Kathleen, I'm so sorry I missed your question earlier. What totals is it that you wanted me to go over before we finish this question? Was it just the ones underneath in each of the overall pieces? I'm sorry, I can't hear you if you're talking to me. So let me see. But if it was the totals, what I did was I just took the area of this triangle, and this rectangle and added them together. Oh, you're talking about like here. Yeah. Okay. So to find those totals, we're just going to take the areas that I found separately, triangle, triangle, rectangle. So that was these 3. So I just have 2 plus 12 plus 2, and that's where we got the 16. And that's this total area right here, both triangles and that rectangle included. Then for this total, I took the area of this triangle and this triangle. So those would be those two, added those together and got a 4. And then for this last total, it would be this triangle plus this triangle, which was a 2 plus a 4 or a 6. Okay. All right. Now we did all that work and we haven't even answered the question that they asked us. This one is brutally long, I know, but luckily there aren't very many of them that are this long. How do we find position from velocity? We integrate. Okay. So what we're going to do, if this is our position function, or pardon me, this is our velocity function, and we want to find position. So what I'm going to do is I'm just going to start integrating. Okay. First things first, here's going to be my position function. How do I find it? All right. This is the velocity function on the time interval from 0 to 1. So I'm going to integrate velocity. If I integrate 4t, I'm going to get 2t squared plus a constant. Now, from our Cal 1 methods, how did we figure out what that constant was? We used a known value. Now you'll have to go all the way back to the top, but the statement of this problem tells us that the initial position is 1. So S of 0 is 1. Okay, so what that means is if this is your position function on this first time interval, and we know that the position at t equals 0 is 1, if we replace t with 0, we would get 2 times 0 squared plus c is equal to 1. So c will be 1. Or my position function for this first bit of our velocity function will be 2t squared plus 1. And that will be position on that first time interval. To find the position on the second time interval, we're going to do the same thing, but we're going to integrate this function. So we're going to integrate 4 dt, which will be 4t plus c. But now what? Well, this function started at 1, and we want them to match up. We want the two functions to match up at the end point. So to find an appropriate constant, I'm going to evaluate the previous position function at the right-hand endpoint. So S of 1 here will be 2 times 1 squared plus 1, which is 3. And I'll use that value to find the C here. So S of t is 4t plus c. S of 1 would be 4 times 1 plus c, and that equals 3. So that would give me that the constant value here would be -1. So my second part of my position function will be 4t minus 1, and that will be the position from 1 to 4. Okay. For the third interval, what we're going to do is we're going to integrate -4t plus 20 dt, and we're going to use the previous position at t equals the right-hand endpoint, because we want to make a match up here at these endpoints that are, I shouldn't say common because it's included here and excluded here, but it's the changeover point, so to speak. So we're going to evaluate this second position function at 4. And we'll use that value to find the constant for our position function. integrate this, we get negative 2t squared plus 20t plus a constant. And we know that s of 4 will be negative 2 times 4 squared plus 20 times 4 plus c, and we want that to be 13. So we have to go through here and evaluate what c would be. So that'll be what? 16 times 2 is negative 32 there, plus 80 plus c is equal to 13.
Man, wouldn't S of 4 be 15?
Oh, good grief, 15. I'm so sorry. I can't add, can I? Thank you for telling me now instead of later. 15. And see, if I had been in a regular class where I could look at you, I could have seen y'all's faces going, how did she get 13? So yeah, you just have to speak up. I appreciate it. All right, so we would have negative 32 plus 80 is what? 48 plus c is 15. So c would be negative 33. So that third part of our position function will be negative 2t squared plus 20t minus 33. And that will be the position function we use from 4 to 6. Okay. Now I'm running out of room on this piece of paper, so I'm going to turn it over so I can use a different part. Well, actually, I'm going to get a different piece. Okay. So we have up to this point. Our velocity function for the next chunk is from 6 to 8, and we're going to use this velocity function. So our position function will be the integral of 4t minus 28 dt, and we will use the position of the previous function at 6. So the position of the previous function at 6 will be s of 6 will be negative 2 times 6 squared plus 20 times 6 minus 33. So I'm getting negative 72 plus 120 minus 33.
Yeah.
Which is what, 15? Because that's negative 105 plus 120. All right, so we will have 2t squared minus 28t plus a constant. And we want, that's our position function in general, and we want s of 6 would be 2 times 6 squared minus 28 times 6 plus c. We want that to equal 15. So we get what? What's that? Let's see, 168. So what are y'all getting for C on that one? Gonna move this up just a little bit.
Maybe 111.
That's what I got. So we'll go with 111. So our position function for that part will be 2t squared minus 28t plus 111. And that's the interval from t equals, or t bigger than 6 to t equals 8. Now, the very last one for this particular problem, we're going from integral of negative 2t plus 20. So we will have s of t equals the integral of negative 2t plus 20 dt. And we'll use the position at t equals 8 of the previous position function that I just erased. I didn't erase, but I hid it from you. Didn't mean to, sorry. So we'll have s of 8. We'll use 2 times 8 squared minus 28 times 8 plus 111. So we're going to get I'm getting 15 again, which is always possible. But so we'll have s of 8 is equal to 15. So when I integrate this, I get negative t squared plus 20t plus a constant, and s of 8 is negative 8 squared plus 20 times 8 plus c, and we want that to be 15. So we've got, oh, sorry, not that y'all could see that. I'm getting negative 81 for C. Is that what you guys are getting? And so our last position function is negative t squared plus 20t minus 81 on the interval from 8 to 10. That one was just kind of mean because they gave us so many different pieces for our function. Area between curves. All right, so section 6.2 is where we're going to talk about just area between curves. And we won't, if it makes you feel any better whatsoever, we won't always do 2 sections a day. There are quite a few days where we do, but particularly as the material gets more, I don't want to say complicated, but more new, so to speak, we'll try to keep it as small as possible, the number of days we have to do 2 or 3 sections, but it does happen. But at least 6.2 is something related to something that we've done before in Calculus 1, and it should be familiar to us. We've talked about this some today, so this part should be fairly quick. Remember, if you have a function that is non-negative over the interval from a to b, and you want to find the area below that function and above the x-axis, kind of the idea we did when we were in Cal 1 was we, on an intuitive level, divided this up into a bunch of little rectangles and then took the limit as the number of rectangles went to infinity. And that was when we, what we talked about with the definite integral notation. So this area would just be the integral from a to b of f of x dx, where f of x minus 0, so this point is f of x, this point is 0, so f of x minus 0 is the height or length of one of the little rectangles, and dx is the width of one of your little representative rectangles. Okay, so we did a bunch of those in chapter 5. What about we're going to do in section 6.2 is we're going to kind of expand this idea so that we're not just finding area between a graph and the x-axis. Maybe we're finding the area between 2 separate graphs or something like that. So we can expand that idea, though, if you think about it. If I gave you this rectangle right here, so this is an f of x and this is a g of x. Could you tell me how to find the height of that rectangle? It's a vertical distance. So like if this was at 3 and this was at -2, could you tell me how tall this rectangle would be? How many units would it be?
5.
5.
What do? You take the top minus the bottom.
Subtract the bottom.
Right, so it'd be 3 minus a negative 2. So the height of this little representative rectangle in general, whether it's this one or this one or this one, to find the height of that, we would just take f of x minus g of x, or that would be the top graph minus the bottom graph. The width of that little representative rectangle is just that horizontal distance, so we still call that dx. So if this is x equals a and this is x equals b, that area of the shaded region would just be the integral from a to b of the height of your rectangles, that f of x minus g of x, dx. It's just that before, most of the time we were finding area between a graph and the x-axis, so the bottom graph or sometimes the top graph was just 0. So we're going to expand in this section to where the top or bottom graph is not just the axis. Okay. So let's say this graph is f of x, and this graph is g of x. What's going to be different on this one?
The g of x will become the top.
Exactly. They switch roles, right? If we're looking between A and B, the top graph is f of x and the bottom graph is g of x. But if we look between B and C, the top graph is g of x and the bottom graph is f of x. So sometimes we have to break it up a bit and do a couple different integrals. If you wanted to find the entire region here, that area would be the integral from A to B of top minus bottom graph dx plus the integral from B to C of top minus bottom. What just happened there, though, was the top graph and the bottom graph switched places because they crossed, okay? So it's going to be very important on these functions to actually draw yourself a picture of the functions. Doesn't have to be perfect, but it is going to have to be good enough that you know which graph is on top versus which graph is on bottom, okay? And if you don't have a graphing calculator, you know, there are lots and lots of free graphing apps that you can use, or free graphing websites that you can go to if you're just looking. A lot of the homework problems actually draw the graph for you. Okay. All right. So we were just looking at ones with X's. Do we always have to add up vertical rectangles? Well, no. It's possible that maybe instead of having a function that is written with x as the independent variable, maybe it's x as a function of y. So I'm going to call this function f of y. It's just as possible to look at adding up horizontal rectangles rather than vertical rectangles. Okay, so for example, if this was, say, x equals 3 and this was 0, then the length of that rectangle would be 3 minus 0, or 3. The important thing is when you're talking about horizontal rectangles, to find the length, or quote height, instead of being top minus bottom graph, it's going to be the right graph minus the left graph. So the area here would be the integral from C to D, because those are the y limits on this region, of f of y minus 0 dy. And the only reason this is 0 is because my region only went back to the x-axis. So this is our right graph minus our left graph. So if this one was f of y and this one was g of y from C to D, this would be the integral from C to D of right graph minus left graph dy. Remember, this is the length or height, so to speak, of the rectangles that we're adding up. This is the width of them or the thickness of them. Okay, so if we're going to be trying to find areas of general regions between curves, first thing that we're going to want to do is graph the region. Okay, we're going to determine whether we want to integrate with respect to X or Y. In other words, do we want to look at vertical rectangles? Do we want to look at horizontal rectangles? And sometimes we'll want to do one, sometimes we'll want to do the other. We'll look at when we do what. Find the limits of integration and then integrate. Okay, so let's suppose, I'm going to rewrite it. We have y equals 3 times x plus 1. Y equals 4 times x plus 1. And x equals 4. So we want to draw the region bounded by these 3 graphs and then find its area. What kind of graphs are all 3 of those equations?
Linear?
They're linear, yeah. So we're going to go, my x units are going to be wider than my y units because I need a bunch more of them. But okay, so I'm going to go by, say, let's see. Let's go by 3s here, 2s. So this would be 18. I'm going by 2s on the y's just so I can get this whole graph on there. All right, so if I graph 3 times x plus 1, that's the same thing as 3x plus 3. So that's a line with a slope of 3 and a y-intercept at the point 0, 3. So when x is equal to 4, I would have 15. So that would be right about there. So there's my graph of y equals 3x plus 3. Now I'm going to graph y equals 4x plus 4. Slope is 4, y-intercept is 4. So I'm going to start here. When x is equal to 4, that's going to be 16 plus 4 is 20. So at x equals 4, that's going to be up here at 20. So that's a little bit steeper graph. Okay, and that's y equals 4x plus 4. And then the line x equals 4, remember x equals 4 is just a vertical line through that x value. So my region enclosed by those 3 graphs looks like this. Is everybody okay right here? Do you have any questions about what I have up to this point?
Can you explain again how to do like the lines, like the 3x plus 3? How do you get like those points over there?
Because you put your y-axis in 2s, and then I got confused when you put your first dot was on, your first y-intercept was on 6.
Yeah.
Dad, that's why
Yeah,
no one. Let's
yeah.
go with that being, yeah. No, it's just because I got off on my units. Yeah, because it's not you, it was me. So let's call that 3 and 4. So
Oh, okay, so this will
just
be
pretend, yeah, like pretend that that's up there. Now, what I'm doing, just because it's going to be a little bit quicker on this one, is I want the area in the first quadrant. Okay. My apologies, guys, because yeah, I just don't have enough room to put it all up there, but let's just go with that's 3 and that's 4. No wonder y'all were confused. And so our graph would, if it had good units, it'd be way up here. But if we were going to do the entire region contained between these graphs, I'd have to go further over here and find the point of intersection. We'll talk about those here in just a minute. But right now, I just want to do what's in the first quadrant. Okay, so going back, did that answer y'all's question about how I got those points now that I labeled them properly?
Yes, no,
Okay.
I got it.
Just wanted to make sure. Sorry, I apologize. Now, Do I want to add up horizontal rectangles or vertical rectangles? Well, since both of my graphs were given with X as the independent variable, I'm probably going to want to try to add up vertical rectangles. So I'm just going to draw myself a few in there and say, okay, do we have a consistent top graph and a consistent bottom graph? Yeah. The line 4x plus 4 is always above the line 3x plus 3 on this region. And so the top graph is always going to be 4x plus 4, and the bottom graph is always going to be 3x plus 3. Okay. Now, like I said, I'm only looking at the first quadrant. Otherwise, we would have had to go ahead and pull this out and find that point of intersection. Just trying to save a little time here. So if we want to find this area, we will integrate from the lower X limit on this region is 0. The upper X limit on this region is 4. So we'll go from 0 to 4. Top graph minus bottom graph would be 4x plus 4 minus 3x plus 3 dx. Now, I'm not going to integrate these just to save time, but I would suggest here, as well as in future problems, most of the time it causes less trouble if you'll go ahead and simplify this before you integrate. So I'd have a 4x minus 3x is x, 4 minus 3 is 1. So we're actually just integrating x plus 1 dx between 0 and 4. Does that make sense? I just find that a lot of times when people leave it like this, they miss a negative sign or something like that. So yeah, you just have to remember that's 4x plus 4 minus 3x minus 3 after you distribute that, and then combine your like terms. Okay. All right. What about this one? Here, this graph is 9 sine x. This graph is 9 cosine x. Will I be able to use vertical rectangles and just use one integral? What's the top graph for this rectangle?
9 sine x.
Correct. What's the top graph for this rectangle?
9 cosine x.
Correct. So we're going to have to break this up. Excuse me. If we're going to integrate this with respect to x, which I would, because how many of you want to solve this for x and bring in inverse cosines and inverse sine? Nobody wants to do that, right? So we do want to integrate this with respect to x, but we are going to have two separate integrals. So it will be imperative that we know what the point is where those two graphs cross. Okay, so we're going to come over here. How do you find a point of intersection? You set the graphs equal to each other. So we'll have 9 sine x equals 9 cosine x. If we cancel out the 9s, we'll have sine x equals cosine x. Now, if it's a nice problem, you know, you'll be able to do it from the unit circle. When is sine and cosine? When are those two equal? Well, that's when your reference angle is a 45-degree angle, or pi over 4. So the first time to the right of the y-axis that sine and cosine are equal is when x equals pi over 4. So this point will be at pi over 4. So for the left half of our region, to find that area, we will have the integral from 0 to pi over 4. Top graph minus bottom graph to find the height of that rectangle would be 9 sine x minus 0. And since this is 0, you don't actually have to write that part down. I just want you to remember you're doing a top minus bottom to find the length of that rectangle. Everything we do as far as distance will be a top minus bottom or a right minus left. But this would be the height of the rectangles and the width is dx. And then to that, we will add the area of this part, which will be from pi over 4 to pi over 2. The top graph is 9 cosine x. The bottom graph is 0, and the width is dx. So you'll integrate 9 sine x from 0 to pi over 4 and 9 cosine x from pi over 4 to pi over 2. So sometimes you can't avoid doing multiple integrals, and that's okay. You just have to draw your graph, look at the region, and see if your top and bottom or right versus left graphs change in the middle of the region.
Can you remind me why -0?
Because what we're doing is we're looking for the height of this rectangle, right? The top, that's just the top y value minus the bottom y value. So this top
Oh,
y
okay,
value,
gotcha.
yeah,
Perfect, thank you.
you bet. All right, so let's look at this one because this one's a little bit weird. In this particular one, they ask us to set it up 2 ways, one with respect to x and one with respect to y. So the region that we're looking for here is this little weird shape right in here. That's what is being shaded. Okay. So I'm going to kind of blow that picture up right over here because that's just too small for me. Okay, so this is the line y equals 9x. This is the parabola y equals x squared minus 10. And the region that we want is right here. So a couple things. First of all, if this is y equals x squared minus 10, then this x value would be the negative square root of 10. This x value would be positive square root of 10, just by setting that equal to 0. We can see from the picture that that's at 0. We need to figure out what this point is. Okay, so I'm going to set x squared minus 10 equal to 9x and solve. So that will be x squared minus 9x minus 10 is equal to 0. And I almost forgot, but for attendance purposes, if you are still here, would you please type here in our chat bar, please? Okay. So we've got x minus 10 times x plus 1 equals 0. So these two graphs, if we were looking at the whole picture, those graphs cross when x is equal to 10 and when x is equal to -1. Based on our picture, the point that we're interested in is where we have a negative x value, so that would be at -1. Okay, so this is point where x is -1, and so y would be 9 times -1 or -9. Now, before I go on, is everybody okay up to this point? Okay. Now, if we are going to do vertical rectangles, in other words, x is the independent variable, I'm going to just draw a few in. And notice that to the left of this vertical line, the top graph is the x-axis and the bottom graph is the parabola. Once I cross that point of intersection, the top graph is the x-axis and the bottom graph is the line. So I am going to be required to do 2 integrals in this particular problem using vertical rectangles. So if we're integrating with respect to x, in other words, adding up vertical rectangles, we will have the integral from x equals negative square root of 10 to x equals -1, which is this point. top graph minus bottom graph would be 0 minus x squared minus 10 dx. This is the height of the rectangles. This is the width. So this part, remember, is a limit of the number of rectangles going to infinity between those two x values. So what we're basically doing is, with this limiting of a sum process, we're adding up the areas of these infinitely many rectangles, like I said, on an intuitive level. And then we'll have plus, pick up here to here. That will be from x equals -1 to 0. The top graph is on the x-axis, which is y equals 0. The bottom graph is on y equals 9x. So it'll be 0 minus 9x dx. Every length of every rectangle will be a top minus bottom or a right minus left. Okay.
How did you get the minus square root of 10?
This graph is x squared minus 10, and that point is just the x-intercept on the left. So when you set x squared minus 10 equal to 0, you get x squared equals 10. So x is either plus or minus the square root of 10. The left
Oh, okay.
one's the negative and the right one's the positive.
Oh, okay, awesome.
All right. So last thing, I know we're about to run out of time. So that's with respect to x. With respect to y, we're going to be looking at horizontal rectangles. Will I need 1 or 2 integrals?
Two.
Do the graphs change spots?
1.
In this particular case, it's a little bit weird to look at, but on this particular region, if we're drawing horizontal rectangles, the line is always on the right and the parabola is always on the left. So we can actually do it with 1 with respect to y, but we're going to have to do something else first. If we're integrating with respect to y, the limits are easy. We go from bottom to top, y goes from -9 to 0. But these are the y limits on our region, so I can't use my functions in terms of x. I'm looking at these little guys are dy as their thickness or their width. So I need to represent my functions as functions of y instead of x. So I'm going to have to solve for x in terms of y. Y equals 9x will be x equals 9 over y. And then, or y over 9, sorry. Y over 9. It's just linear. Or 1/9 y if you prefer. And this y equals x squared minus 10. If we solve that for x, that's y plus 10 is equal to x squared. So x will be either plus or minus the square root of y plus 10. Now, which one do we have? X is positive to the right of the y-axis. It's negative to the left of the y-axis. Since we're looking at a region to the left, this part would be x equals negative the square root of y plus 10. So we will have the right graph is y over 9 minus the left graph is negative the square root of y plus 10. The thickness is dy, and we would be integrating from -9 to 0. Now, on your homework, they'll ask you to actually do the integral. Now, I would just pick whichever one is easiest to do. For me, I'd probably do this one instead of the x's because it's a little bit shorter, but either way you go will be fine.